Oh, don't mind me. I'm just changing the color of my crayon. Anyway, on 8. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Remember, step 1 is to draw a picture. And voila, I've done so. So this is one of those, of course, that they gave to us with a picture, and they have also captioned it because we wouldn't be able to tell what the heck this whole thing was without that caption inflating a balloon. Maybe I label some stuff on here. So we have some sort of radius here. That radius is increasing. It's getting bigger and bigger, and as it does so, the volume, of course, increases as well, the amount of air being pumped in. So let's now list out all the stuff that we have. What's the first number that we have? We've got 4.5. Notice the units, cubic feet per minute. So that kind of clues us into what kind of quantity is changing. What's being measured here? Cubic feet? It says air. Notice it doesn't say volume anywhere, but that's the implication whenever our units are in cubic feet. So it is right with the laser, dV dt is equal to 4.5 cubic feet per minute. And then what is the next number? It doesn't give us a next number. Instead, it gives us find. I meant to do that with a laser. So I highlight with a pencil, a crayon, but then I write with a laser because that's what I do. Anyway, find the rate of change of the radius. So I'm going to stop right there and say that I am looking for a dr dt is equal to question mark. And then find, when the radius is 2 feet. So we have r is equal to 2 feet. Question, when is the radius equal to 2 feet? Always? No, at a particular instant. The clue there is that when it happens. When it happens at a particular instant, which means that we do not plug that 2 in until after we're done differentiating. Otherwise, it's just going to go to 0. It's going to mess everything up. Okay, so I think that we've got all of the quantities that we need. Let's go ahead and come up with an equation that's going to relate these rates together. We're talking about a volume of a spherical balloon, so does it make sense that we should differentiate the volume formula for a sphere? And that is V is equal to 4/3 pi r cubed. If you don't believe me, look at that worksheet that you had to fill out before starting all of this process, right? Okay. Who was your geometry teacher? Did he teach you such a formula? I hope he did. Or she. I mean, whatever. Okay. Anyway, so I've got all my quantities. I've got my equation. I'm ready to take the derivative with respect to time. And come on. There we go. All right. So the derivative of the volume on the left-hand side, we got a dV dt. And then on the right-hand side, there's no reason to use like a product rule or a quotient rule on this because the 4/3 pi is just a coefficient on the r cubed. And it's not like we got a second function up in there. So when we leapfrog the 3 down, it's going to cancel with the 3 in the denominator, giving us 4 pi r squared times dr dt. I think we mentioned in another video, perhaps, I don't know, maybe, that the rate at which the volume, is changing is related to the surface area of the sphere. Interesting. All right. Now, what are we looking for again? Remind me. We're looking for a dr dt. So I'm going to suggest that we go ahead and isolate a dr dt. Should be pretty simple because all we have to do is divide the 4 pi r squared over to the other side. So our dr dt is equal to dv dt divided by 4 pi r squared. Ta-da! Not quite done yet. Now we just got to substitute stuff in. Calculus is pretty much done. The rest is just some arithmetic. Okay, so dr dt will be equal to, specifically, let's see, that was 4.5, wasn't it? 4.5, yes. Over 4 pi times my radius, I think it was 2. Yes, it was. Yeah. There we go. Is it safe stoppable? Sure it is. Should we get the practice doing the arithmetic? Sure we should. Oh, whoa. I guess it would be safe stoppable now after I square the 2 anyway. So we can do our arithmetic here on this example. It's not as obnoxious as the oil slick question, that's for sure. All right, so we've got 2 squared is 4. 4 times this other 4 here gives us a 16 pi. And you can leave it like that if you desire. Or we could fix the complex fraction that happens when having a decimal inside of a fraction by multiplying it by 2 over 2. Fancy one? I was about to say fancy 0. Don't multiply by a fancy 0. Okay, so up top we're going to have a 9, and on the bottom a 32 pi. Now, let's figure out our units. Okay, on this equation here, the actual derivative equation after we have isolated the dr dt, this is the best one to use, dv dt is being measured in cubic feet per time thingy. I'm pretty sure that time thingy was minutes, okay? And on the bottom, the only quantity that we have that's changing is the radius, and the radius is being squared, so divided by feet squared. Okay, feet cubed divided by feet squared gives us feet. And the minute sticks around. Does it make sense? Here, let's look at this. dr dt. Well, r is changing by feet as measured in feet, and the time is being measured in minutes. Seems to make sense to me. All right, so just recap this. If I had to write some sort of sentence, I would write that at the instant when the radius is 2 feet, then the radius of that balloon is increasing at a rate of 9/32 piths, that's how you say that, feet per minute.